Now, we earlier saw the Pelly-Robson chart as a way of measuring contrast, but vision scientists tend to measure contrast in a somewhat different way. We measure the contrast sensitivity function. And this image here is a really nice way of enabling you to immediately see your own contrast sensitivity function. So let me talk you through what this image shows. It actually shows across each pixel row, so from left to right here, as you can see, the luminance is going from high to low to high to low and so on. And as we go from left to right, the spatial frequency of those alternations is increasing. Now, as we go up and down the image, the contrast varies. So at the bottom of the picture, we have high contrast, so the pixels are going from white to black to white to black. And as we move up, they're starting to go from light grey to dark grey to light grey to dark grey and so on. And right at the top of the screen, it's just a uniform grey. All right? The important thing to know about this image is that the luminance variation in any one pixel row is actually constant all the way across the screen from left to right. But I'm guessing that's not what you see. If I were to ask you to draw the point at which you see the stripes fade into grey, you would probably draw something like this. So the stripes appear to go up much further in the middle of this image than at either the left or the right. But what I want to bring home to you is that that's nothing to do with the values of the luminance on the screen. That is, as it were, an illusion within your own visual system, and it reflects your particular contrast sensitivity function. So this is because the human visual system has got much less sensitivity to low and high spatial frequencies than it does in the middle. So let's talk about the idea of threshold contrast. Threshold contrast is defined as the minimum contrast that we need to see the grating. So let's say the threshold is this blue line here. Above this point, the variations from bright to dark are below threshold. So this person whose threshold this is can't see the variation here. Whereas down here, the variation's above threshold, and so they can see it. Contrast sensitivity is simply defined as 1 over the threshold contrast. So if your threshold is low, that means your vision's really good and your sensitivity is high. If your threshold's high, that means we need to provide a lot of contrast before you can see something because your sensitivity is low. So this graph is drawn so that sensitivity is highest at the top and lowest at the bottom. So here we have high sensitivity, very low threshold, little contrast is needed, and down here we've got lots of contrast is needed, and therefore you've got low sensitivity. But don't forget that the contrast, the physical quantity, is the same for all points at a given pixel row. So here and here, the contrast is the same. The only difference is that this contrast is just at threshold, so very hard to see, whereas this contrast is a long way above the person's threshold and therefore much easier to see. Don't confuse contrast with contrast threshold. It's worth talking in a little more detail about this concept of threshold contrast. I defined it earlier as the minimum contrast which you need in order to be able to see the stripes. But that's a bit of a woolly definition. It's not as if I go abruptly from not seeing the stripes and then you increase the contrast a tiny bit and now I see them perfectly clearly. If you do an experiment where you measure this in the vision science lab, one way of doing it is to ask people, you show them either stripes or a blank screen, and you ask them to report, do they see the stripes or do they see a blank screen, by pressing a button, say. Now you'd imagine that when you put up a truly blank screen, so the contrast is 0, they should always report seeing a blank screen. And they basically do, except they have a small false positive rate. So this might be because they've made a mistake pressing the button. It might also be to do with where they set their decision criterion, so they're looking very hard going, do I see stripes? Yeah, I think I do. And sometimes they will report seeing stripes even when there were none there to see. So that's their false positive rate. When the contrast's really high, you would hope that they would tell you every time, yes, I see those stripes. But again, humans are humans, and so every now and again they press the wrong button and we get a false negative rate. And in between, at intermediate contrasts, the frequency of reporting that they see the stripes rises smoothly from this false positive to the false negative rate. And at some point in the middle, traditionally at 50%, you can define a threshold contrast. And so that tells you where on this curve am I going to define my threshold. And that's a rigorous and quantifiable way of defining the threshold contrast. So as I pointed out, as that contrast sensitivity curve shows, we don't see all spatial frequencies equally well. We need more contrast in order to perceive high or low spatial frequencies. And actually, if you go back and view this screen from a long way away, maybe you can't see the fine black and white stripes here. Maybe this patch is already blurring into grey for you. So why is the contrast sensitivity function so important? Why do vision scientists go on about it so much? On the face of it, all it's telling us about is the visibility of sinusoidal luminance gratings, which you may be thinking are a fairly artificial thing and not very relevant to vision in the real world. Well, the answer to that is going to take us down a little bit of a diversion. We're going to be talking about Fourier analysis and the remarkable fact that any image can be expressed as a sum of sinusoidal luminance gratings, which immediately makes them much more relevant than they might have appeared so far. So here's an image. This is a photograph of Newcastle's Tyne Bridge, which I took. It's a very big image, so to make things simpler, I'm just going to downsample it, or part of it, to 40 by 40 pixels, and also I'll make it black and white so I don't have to worry about the different colour channels. Okay, so this is hopefully still just about recognisable as a piece of the Tyne Bridge. Now I can take that image and I can compute what's called its Fourier spectrum, and that's what's shown here. We've got an amplitude and a phase. And what a Fourier spectrum is, it tells me how much of each different sort of sinusoidal grating I need in order to reconstruct that image of the Tyne Bridge. So each pixel in this Fourier spectrum represents one grating. Points closer to the origin represent low spatial frequencies. So this point here represents this grating. You can see that's quite low frequency. This point out here, it's a lot further from the origin. It represents this grating, which is a lot higher spatial frequency. You can see the stripes are much closer together. The polar angle, so where we are around the clock, reflects the orientation of this grating. So points on the y-axis represent horizontal gratings, points on the x-axis represent vertical gratings, and points in between represent oblique gratings. Now the colour assigned to each pixel represents how much of that particular grating we need to add in order to reconstruct the image that we started off with. So in the next several slides I'm going to go through this Fourier spectrum. I'm going to start off by picking the grating component with the highest amplitude. So that's one of these white pixels near the beginning, near the origin here. I'll call that component number 1. I've actually marked the pixel with a little white ring around it, although it's rather hard to see at the moment. So that's the Fourier spectrum. This is the original image we're going to try and get back to. This is the first component, so it's a horizontal grating, very low spatial frequency, and with this particular phase, so the phase of a grating refers to where the dark and the light are. So the phase of this grating is such that it's got dark at the top and bright on the bottom. Now over here I'm going to show the grating going from black to white every time, just so that you can see it very clearly. But over here I'm going to have the true amplitude, so once it's actually been multiplied by the correct value that I need to put in the image. And you can see that that's now much smaller, so rather than going from black to white, it's actually going from dark grey to light grey here. And the next row I'm going to show the sum of all the components we've got so far. At the moment there is only one, so that's the same. Okay. Now obviously where we've got to at this point does not look very like the original image, but you might be able to see that even now it's got some kind of approximation to the image. At the very least it's got darkness in the top half of the image and brightness in the bottom. So to that extent it's already starting to capture something about the original image. But that's only one component, remember, and we do have a lot more. So now let's go on to the second component. This is also a horizontal grating, but now it's of a somewhat higher frequency. Again, scaled down, the amplitude we're actually going to add in is much, much smaller. And now down here I'm showing the sum of the two components that we've got to so far, again normalised so that we go from black to white and in the actual amplitude that they're going to show up in the image. Okay, that's component 2. Now we're going to go to component 3, so defined as the one with the third largest amplitude, and this time we have an oblique grating. Okay, there it is, scaled down, and now we've got the sum of those three components all together. There's component 4, okay, component 5, another oblique grating, 6, 7, 8, 9, 10. Now you get the idea, so now let's speed things up a bit, adding in more and more components. So it's the same kind of idea. You can see the white markers here are showing you which component we're currently adding. They always occur in pairs on either side of the origin like that. The true amplitude is getting less and less, you can barely see it, and yet over time the sum is changing and it's now starting to look much more like the Tyne Bridge. You can see the structure of the image emerging. And now let's speed it up even more and go through the remaining components. And really now you can see that we're just at the stage of removing noise effectively. The image already looks very close to the final one, but we've just got some speckle in the sky which these higher components are really removing. And you can see the frequencies now are very high. There you go, and that's the result after all 800 components. So I hope that was at least partly clear, but don't worry if you found it hard going. Really just what I wanted you to take away was the idea that any image can be expressed as a sum of sinusoidal luminance gratings. And because the early human visual system is at least roughly linear, what that means is if we want to know what we can see in general, we just have to measure what sine gratings we can see, and then we can deduce what we'll be able to see in any image. So this contrast sensitivity function is absolutely fundamental to measuring and assessing our vision. It really tells us a huge amount about our visual abilities, and that's why I'm banging on about it so much. So there it is, the contrast sensitivity function.